So hi everyone, I am Subhadip. So today in this video, I will explain Rolle's theorem and Lagrange's theorem with some examples and geometrical interpretation of both of these theorem. And I hope after this video it will be crystal clear to you, right? So first of all, let us find the statement of Rolle's theorem. So what is Rolle's theorem? So let f is a function defined from AB to R such that this function f is continuous on this interval. That means f is continuous on this closed interval AB. And second one is f is differentiable on open interval AB. And third condition is fa equals to fb, then there exists some c belongs to open interval AB such that f dash c equals to 0. So this is the statement of the Rolle's theorem. Now we are going to find the geometrical interpretation of this theorem. So geometrically, what does it mean by this theorem? So let us draw the coordinate axis. So this is our coordinate axis y and this is x, right? So this is x o x dash and y o y dash. Now we are taking some function this, where this function is continuous. Clearly this function is continuous because there is no break in AB. So suppose this is A and this is B. So this function is continuous on AB, differentiable because we can draw unique tangent on open interval AB to this curve. So this is also differentiable, and also from the graph we can see that FA is FB. Then what will happen? F dash C will be 0 for this graph. So f dash C is nothing but the slope of tangent at C. So this is some point C is between A and B, and this is 0. That means the slope of the tangent at the point C will be parallel to x-axis because slope of x-axis is 0 and this tangent of at C is also 0. Slope of the tangent at C is also 0, so it will be parallel. So these things. Now one can ask this question: if this point C is only one point, or there is many point for another function we can find. So let us draw another figure. So this is if it is. So suppose now our function is like this, right? So this is suppose A FA and this is B FB. So here also we can see that this function is continuous on AB, and this function is differentiable because we can draw unique tangent at any point C on the interval open interval AB. So it is differentiable on open interval AB. So we can draw some tangent at C. So here not only one point, we can find here also a point. This is parallel to x-axis. Here we can draw a parallel to x-axis, and here also we can find one tangent which is parallel to x-axis. So these things, geometrical interpretation of the Rolle's theorem. Now let us take an mathematical example. Suppose fx is our x square plus 2 on the interval -2 to 2. So we apply Rolle's theorem here. We are going to see if the Rolle's theorem applicable for this function or not, right? So here fx is continuous. Because why this is continuous? Because this is an polynomial function, so it is continuous on -2, 2. And then fx is also differentiable. Why it is differentiable? Because this is also a polynomial function, so we can find that differentiability. So this is minus on open interval, obviously minus 2 to 2, and also we can find that f of minus 2 is minus 2 whole square plus 2, so this is 6, and this is also f of 2. So these three conditions satisfied. So now we are going to see if there exists a c on that interval minus ab to a minus 2 to 2, where f dash x f dash c is 0. So what is f dash x here? F dash x is 2x. Now let c belongs to this minus 2 to 2 such that f dash c is 0. That means 2c is 0. So what is our c? C is our 0, and we can see that this 0 belongs to this interval minus 2 comma 2, right? So Rolle's theorem is applicable for this function. Okay, now we are going to find some functions where the Rolle's theorem is not applicable, and by this example we also can find that how much these all three conditions are important, right? So suppose our fx is mod x, so what will be the function? This function is like this. So this is our mod x function, x dash x y dash, right? So this is our mod x function, and clearly we can see that if we take some interval like minus 1 to 1, so we can see that this function, if we take this is so here the function is continuous. Why continuous? We can see from the figure also we can find here like this. So when this is x, when x greater than equals to 0, and minus x when x lesser equals to 0. Now if we find limit x tends to 0 fx, this will be limit x tends to 0 x, so this will be 0, and also limit, this is 0 plus, and limit x tends to 0 minus fx, so this will be also what? Limit x tends to 0 minus x, so this will be also 0. So this function is continuous on this interval. Now for differentiability, let us check the differentiability. So L f dash 0 equals to limit h tends to 0 minus f of 0 plus h minus f of 0 divided by h. So this will be limit h tends to 0 minus f of h minus f of 0 means 0 divided by h. So 0 minus, so left side, that means minus h. So this is limit h tends to 0 minus h divided by h, this is minus 1. And for right hand derivative, what is r f dash 0? So this will be limit h tends to 0 plus f of 0 plus h, that means h minus f of 0 divided by h. So for right hand side, so this will be limit h tends to 0 plus, this will be what? H minus 0 by h, so this is 1. So we can see that L f dash 0 is not equals to R f dash 0, that means this function is not differentiable. We can see it from here also, because we cannot draw unique tangent at 0. There may be more tangent, there is more tangent, it is not unique tangent, so it is not differentiable. So since it is not differentiable, so Rolle's theorem is not applicable, and we cannot find some c that is parallel to some that is parallel to x-axis, right? So this is an example. One more example we are taking where Rolle's theorem is not satisfied. Suppose fx equals to x and this is 0 to some 2. So let us draw this function also. So this is our function y equals to x, that is f of x equals to x. Now 0 to 2, so this is 2. Here we can see that their function x is a polynomial function, so it is continuous. First condition satisfied. Second condition, differentiable on open interval AB, so this is also satisfied. Now third condition is f of 0 is our 0, but f of 2 is what? F of 2 is 2. So this is not satisfied, so we cannot find some c such that f dash c is 0 here. So these are the examples where Rolle's theorem are not applicable. Now one question may arise that the converse part of this theorem, this is converse of Rolle's theorem, is that true? Converse of Rolle's theorem is true. So first of all, what is converse of Rolle's theorem? So suppose f is a function from ab to some r, and such that there exists some c belongs to this open interval ab such that f dash c is 0. Then what will happen? First condition, f is continuous on this open interval ab. Second condition is f is differentiable on this open interval ab, and third one is fa equals to fb. So this is the converse of Rolle's theorem, but this need not be true. Need not be true. So this converse of Rolle's theorem need not be true. Why? Let's take an example. So suppose this is our coordinate axis, y dash, x dash. Now we are defining some function like this. Suppose this is our a point, this is our some point c where we can draw a tangent. Now here some point d where the function is not defined, like this, and then this. So suppose like this, right? So this is our some function, this is a point and this is our b point, right? Now we can see that we have found that point some c where f dash c is 0, but we can see that this function is not continuous on the closed interval ab because here is a jump. So Rolle's theorem need not be, converse of Rolle's theorem need not be true, right? So this is all about Rolle's theorem. Now we are going to Lagrange's theorem, right? So what is Lagrange's theorem? Lagrange's theorem. So this is a generalization, kind of generalization of Rolle's theorem. So suppose f is a function ab to some r, this is r is a real number, such that first condition is fx is continuous. So this fx function is continuous on closed interval ab. Second is fx is differentiable, this is differentiable on open interval ab. Then there exists some c belongs to open interval ab such that we can write f dash c equals to fb minus fa divided by b minus a, right? Now in that case we also find the geometrical interpretation. So what is geometrical interpretation? We know what is f dash c. F dash c is nothing but the slope of the tangent at some point c. Now we have to find what is the meaning of this fb minus fa by b minus a. So in that case let us draw the figure first of all. So this is our function, suppose like this, right? So this is a point AFA and this is our VFV. Now we are joining these 2 points. So this. So now we know that this if we name this P and this is Q, what will be the slope of PQ? So what is slope of PQ? So slope of PQ will be nothing but y2 minus y1. Here y2 is FB minus FA divided by B minus A, right? y2 minus y1 by x2 minus x1. So this is nothing but slope of the line joining P and Q, where PQ is AFA BAP. Now this line slope of this line and f dash c is same. That means we can find some c where this at c the tangent will be parallel to the line pq, right? So this will be the geometrical interpretation. So we suppose this is c1, we can find also here also. So this is also c2 point and this is also parallel to this line. So this is the geometrical interpretation of Lagrange's theorem. That is, if we take some function and we take point P, P is our AFA and Q is our B, FB. Now if this function is continuous on closed interval AB and differentiable at on this open interval AB, then the slope of the tangent joining this PQ will be the same of slope at some point C of the tangent, right? So these things, so that is this is parallel to the line PQ. So this will be the geometrical interpretation for the Lagrange's theorem. Now let us look at some mathematical examples. So suppose our fx function is same function we are taking as we take in Rolle's theorem. So this, and now we are taking the interval is 0 1, right? So we are taking 0 1 interval. So what this is continuous, since it is a, so first condition continuity satisfied, continuous on 0 1. Then second condition is differentiable, so this is also satisfied on open interval. Then what we find, some c, for some c, so f dash x is what, 2x. So 2c will be f of 1 minus f of 0 by 1 minus 0. So what is f of 1? F of 1 means 3 minus f of 0 means by 1, right? So f of 1 is 3, f of 0 is 2 minus by 1. So c is 1 by 2. Now we can see that this 1 by 2 is inside 0 1. So for this function Lagrange's theorem is applicable, right? So this is the thing. Now we are going to give some real life example for this Lagrange's theorem, right? So suppose this is our city Hyderabad and this is our city Chennai, right? Now let us suppose the distance, this is not accurate, suppose this is some 160 kilometers, right? Now one person from Hyderabad is going to Chennai with some velocity, we don't know the velocity, and here in speed breaker it is given that you cannot cross the velocity 70 km per hour, right? If you cross this velocity 70 km per hour, then you will be arrested and you will have to give some fine like this, right? So let's suppose that here is some policeman is there, right? And here is also some policeman. They are checking if someone is crossing this speed or not, right? So from here, suppose you start at 0 and you arrived here at within 2 hours, right? Within 2 hours you arrived here. So how Lagrange's theorem will be applicable here, so that they will find if you cross the speed limit or not. So here we are talking about the interval 0 to 2 because we are talking time interval 0 to 2. Now what is f of 0? F of 0 means distance. So when f of 0 is 0, our distance is 0. Now f of 2 is what? F of 2 is 160. So this is 160. Now f dash c is what? fb, that means f of 2 minus f of 0 divided by 2 minus 0. So this is 160 divided by 2, that means 80. Now what is f dash c represent? F dash c represent that some instantaneous change at c, right? That means here some instantaneous velocity at c, and this is what? This is average velocity, right? Now average velocity we get 80, and this is some instantaneous velocity, right? Now speed, in speed breaker it is given that you cannot cross this limit 80, but average velocity is 80. That means somewhere this person crossed the limit 70, because instantaneous velocity is also 80 here we get. So you have to give fine or you will be arrested, right? So this is the some kind of exam, some kind of application of Lagrange's theorem, right? Lagrange's theorem, we can say that. So this is it for Lagrange's theorem and Rolle's theorem. I think this is enough for your class 12 sort of, you know, this is enough for the class 12 syllabus, and thank you for watching this video. I hope it is crystal clear now, and if you have any doubt you can ask in comment section. And thank you everyone for watching this video again. Bye.